to 1761. Any of you here have Bayes in any of your classes? None? Okay. Don't worry about it. The best strategy depends on belief or prior knowledge of probabilities of the states of nature. That was the probability of rain and the probability of sun. Best strategy can differ for individuals. That's okay, because you have different assumptions about those probabilities. And there's a neat graphical solution, as we saw on the previous slide. But that's all right. But you can abstract from the rain, the sun, and the three dress actions to very complicated decision problems, like should I invest $500 million in developing a new car line? All the elements that I have in my decision problem for that new car line are here in the rain problem. Now, the only thing is, the state of natures here were discrete. There were only two. And so I could do it with algebra. If the states of nature are continuous, those of you that are taking calculus, this problem would be reformulated and the solution would involve calculus. The ideas would be the same, but you move from discrete to continuous variables, and that takes you into calculus. Geometry, we use plane geometry. If you put in more states of nature, it'll become multivariate geometry. You'll have 2 dimensions, 3 dimensions, 4 dimensions. So the math complexity goes up a bit, the ideas are the same. What if you don't have the prior knowledge of rain or sun? What do? Well, many times what we do is consider the worst possible thing that could happen. And then we pick the strategy that minimizes the worst possible thing that could happen. This is called the mini-max strategy. It minimizes the maximum damage that can be done to you. And sometimes it's called a pessimistic or a conservative approach. You're thinking of the worst thing that can happen, and then you choose the strategy that makes that the least impactful. This is our admissible strategies. When I say think about the worst thing that can happen, well, for S1, the worst thing that can happen is rain. For S2, the worst thing that could happen was rain. Rain, 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 sun is 2.2. And so this would be the strategy, S18 would be the strategy that minimizes the worst risk that could happen. And you do that if you had no idea what the probability of rain and sun would be. So that's another option to you. It's a neat way to solve it geometrically also. You simply draw a line, y is equal to x, and then you put an arrow on it. And then you just let that arrow increase. And then you choose the strategy that's first hit by the boundaries of the strategy. And that's the min-max strategy, and it was S18 in this case. Okay. Recap the math. What math did we use here? Well, multiplication rule. How many strategies? 3 times 3 times 3, which was 27. Linear equations and weighted averages. That's the way we calculated the risk. That's algebra. Geometry. We use geometry to plot the risk profiles and then geometrically determine the best strategy, the Bayes risk or the min-max risk. In technical terms, we were looking at convex sets that define the admissible strategies. You probably haven't talked about that in your classes yet, but it's a geometric concept. We use simultaneous equations. Presumably you all had Algebra 2 where you solve simultaneous linear equations. That was used here. We talked about probabilities. Those of you that have taken statistics or AP statistics will certainly talk about probabilities. It comes into play here. And we didn't talk about mixed or randomized strategies. That's a topic for another day. Again, what were the ingredients for a decision problem? You had to have options. The options had to have consequences. We call them losses. There's uncertainty. The outcomes don't guarantee success, but you look for a strategy that gives you a high batting average. That is, if you applied this strategy over and over and over and over again, you would have your average losses would be lower than any other strategy. And so that's sort of the contents of these decision problems. There's a great book that talks about this. It's Elementary Decision Theory by Herman Chernoff and Moses. It's an old book. It was written in 1959 and republished in 1986. But it's devoted to this topic at about this level. So that's a reference for you if you're interested. Well, that's it. Thanks for being such a good audience. Do much better than their competitors. And you should learn tonight, dressed appropriately based on what the weather forecaster decides. And you ought to know how to do that now. Okay. What? Okay. Go ahead. Come up here so I can hear you.
This awful.
I'm a lucky now.